Welcome! In this video, we'll explore an interesting problem titled Count All Valid Pickup and Delivery Options. This is a fascinating combinatorics problem that challenges us to compute the number of valid sequences for pickups and deliveries, ensuring that deliveries always follow their corresponding pickups. Let's dive in. In this problem, we are tasked with counting all the valid sequences of pickup and delivery operations for a given number of orders, denoted as n. Each order consists of two events, a pickup and a corresponding delivery. The rules are straightforward but critical. First, for any given order, the pickup must occur before its delivery in the sequence. Second, no delivery can happen before its corresponding pickup has been completed. These constraints ensure that the sequences are valid. Since the number of possible sequences can grow extremely large as n increases, the result must be returned modulo 10 to the power of 9 plus 7. We're given the input as an integer n, which can range from 1 to 500, and the output is an integer representing the total number of valid sequences mod 10 to the power of 9 plus 7. Let's look at a couple of examples to make the problem clearer. If we have just one order, where n equals 1, there's only one valid sequence, first the pickup, then the delivery. So, the output in this case is simply 1. Now, consider the case when n equals 2. Here, we have two orders, and there are multiple ways to arrange the events while ensuring that each pickup occurs before its corresponding delivery and that no delivery happens out of order. The output for this case is 6, indicating 6 valid sequences. For n equals 2, the 6 valid sequences are as follows. We can pick up both orders first, then deliver them in the same order they were picked up, or we can pick up both orders and deliver them in reverse order. Similarly, we can alternate the pickups and deliveries, as long as each pickup precedes its delivery. These combinations result in 6 distinct valid sequences. When n increases to 3, the number of valid sequences grows significantly due to the additional complexity of arranging 3 pickups and 3 deliveries. For n equals 3, there are exactly 90 valid sequences that satisfy the conditions. The constraints for this problem are important to consider. The value of n can range from 1 to 500, which means our solution must handle very large inputs efficiently. Additionally, the result must be returned modulo 10 to the power of 9 plus 7 to ensure it fits within standard integer limits and avoids overflow. Some edge cases to think about include when n equals 1, where the solution is trivial since there's only one order, and when n equals 500, where the number of possible sequences becomes extraordinarily large. Efficient computation and the use of modular arithmetic are key to solving this problem within the constraints. To solve this problem, we first considered a brute force approach. The idea here is straightforward: generate all possible sequences of pickups and deliveries, and then filter out the invalid ones. Specifically, we would create all permutations of the 2n actions, where each order has one pickup and one delivery. For each sequence, we would then check if the pickup for every order comes before its corresponding delivery. While this approach is conceptually simple, the computational cost is overwhelming. Generating the permutations alone has a factorial time complexity of O(2n), and validating each sequence adds an additional O(n) per sequence. This results in a total complexity of O(2n). (n), which grows too quickly to handle even moderate values of n due to this inefficiency, especially for larger inputs. This approach is impractical and was not chosen as our solution. Next, we explored a dynamic programming approach, which is far more efficient but introduces a level of complexity. The intuition behind this method is to use previously computed results to calculate the number of valid sequences for any given n. For n orders, there are 2n slots, and the first slot must always be a pickup. Once we place this pickup, there are 2n1 slots left. The corresponding delivery can then occupy any of these 2n1 positions. By reducing the problem in this way, we are left with n1 orders to process. To implement this, we define dp I as the number of valid sequences for I orders. Using the relation dp I equals dp I1 asterisk 2I1 asterisk I, and starting with a base case of dp 0 equals 1, we can compute dp n iteratively. The time complexity of this solution is O(n), and it requires O(n) space. While efficient, this approach is more complex than necessary, especially when compared to a purely combinatorial solution. The combinatorial approach simplifies the problem significantly while maintaining optimal efficiency. Here, we use mathematical reasoning to directly compute the number of valid sequences. For n orders, there are 2n slots in total. The first pickup can go in any of these 2n slots, and the corresponding delivery in any of the remaining 2n1 slots. This pattern continues, with each subsequent order having fewer available slots, leading to a product of 2n1, 2n3, and so on, down to 1. This product corresponds to 2n divided by 2 to the power of n asterisk n. To avoid issues with large numbers, we use modular arithmetic with mod set to 10 to the power of 9 plus 7. The implementation is straightforward: initialize the result to 1, and for each order from 1 to n, multiply by 2i1 asterisk I, taking modulo mod at each step. This approach is optimal, with a time complexity of O(n) and a space complexity of O(1). Its simplicity and efficiency make it an excellent choice. Ultimately, the combinatorial approach was chosen as our solution due to its simplicity, efficiency, and minimal resource usage. It takes advantage of mathematical insights to transform the problem into a straightforward iterative computation. While the dynamic programming solution is also efficient, it adds unnecessary complexity and requires additional space. The brute force method, on the other hand, is entirely infeasible for larger inputs due to its exponential growth in computations. By leveraging combinatorial reasoning alongside modular arithmetic, we achieve an elegant solution that is not only optimal but also robust enough to handle large inputs, such as n up to 500. This problem challenges us to count all valid sequences of pickup and delivery tasks, where we have n pickups and n deliveries to complete. The key constraints are that each delivery must occur after its corresponding pickup, and deliveries cannot be interleaved incorrectly. For instance, delivery D1 cannot come before pickup P2. A straightforward approach to solving this involves generating all permutations of the 2n actions, then filtering the valid sequences. To implement this, we can represent pickups as P1, P2, Pn and deliveries as D1, D2, Dn. For example, if n equals 2, the actions would be P1, P2, D1, D2. By generating all permutations of these actions and validating each sequence against the constraints, we can count how many sequences are valid. However, this brute force method becomes inefficient as n increases, because the total number of permutations grows factorially, reaching O(n). Let's explore a smarter approach next. Instead of brute forcing through all permutations, we can use an optimized recursive approach combined with backtracking to directly construct valid sequences. The idea is to define a recursive function, count_sequences, pickups_remaining, deliveries_remaining, which tracks how many pickups and deliveries are yet to be added. We start with all n pickups and deliveries available. The base case for this function occurs when no pickups or deliveries remain, meaning we've formed a valid sequence and can return one. In the recursive case, if pickups are still available, we can add 1 to the sequence and recurse with one fewer pickup. For deliveries, we can only add a delivery if its corresponding pickup has already been added. This ensures validity. This is checked by ensuring deliveries_remaining pickups_remaining before adding a delivery and recursing. To avoid redundant computations, the results of each state, pickups_remaining, deliveries_remaining, are memoized. This eliminates repeated work and drastically reduces the computational complexity. By initializing the function with count_sequences, n, we can efficiently count all valid sequences. The recursive approach offers several key insights. First, the main constraint that each delivery must occur after its corresponding pickup eliminates a vast number of invalid permutations, making this method far more efficient than the brute force approach. Instead of generating O(n) permutations, we directly construct only valid sequences. Second, by leveraging memoization, we avoid recalculating results for the same pickups_remaining, deliveries_remaining state, which reduces the time complexity to O(n²). This is because there are at most n*n unique states to compute. Moreover, the problem has an interesting mathematical equivalence to the nth Catalan number, which counts various combinatorial structures, including valid parentheses sequences or paths in a grid. Data structures such as the recursive call stack and a memoization table are crucial for implementing this approach. The call stack helps explore sequences step by step, while the memoization table stores intermediate results for optimal reuse. The resulting time complexity is O(n) squared due to memoization, and the space complexity is also O(n) squared for the table, with an additional O(n) for the recursion stack depth. Let's solidify this concept with an example where n equals 2. Here, we have 2 pickups and 2 deliveries, P1, P2, D1, D2. We begin with count_sequences, 2, 2, where both pickups and deliveries are available. First, we add P1, transitioning to count_sequences, 1, 2. Then, we add P2, leading to count_sequences, 0, 2. At this point, all pickups are used, so we proceed by adding D2, giving count_sequences, 0, 1. Finally, we add D1, reaching count_sequences, 0, 0, which is a valid sequence. By backtracking and exploring other valid paths, we find all 6 valid sequences for n equals 2, P1 P2 D2 D1, P1 P2 D1 D2, P1 D1 P2 D2, P2 P1 D1 D2, P2 P1 D2 D1, and P1 D2 P2 D1. This systematic construction ensures no invalid sequences are generated, and the total count of valid sequences is 6. This example highlights the efficiency and correctness of the recursive approach with backtracking and memoization. The solution calculates the total number of valid pickup and delivery sequences for n pairs using a mathematical approach. The problem boils down to a combinatorial counting problem where we need to ensure that each delivery action happens after its corresponding pickup. We use a loop to iterate from 1 to n, progressively building the solution. The base case is when there are 0 pairs, the number of valid sequences is 1. For each step I, from 2 to n, we calculate the number of valid sequences by considering the possible positions for the new pickup and delivery pair. Each new delivery can be inserted into 2*i1 positions, and each new pickup has I positions. Therefore, the number of new arrangements is 2*1*i, and we multiply this by the result from the previous step. To prevent integer overflow, we take the modulo of the result with 10 to the power of 9 plus 7 at each step. This ensures that the computation remains efficient and within the problem's constraints. Finally, the result contains the total number of valid sequences for n pairs. This is the Java implementation of the LeetCode problem number 1359, count all valid pickup and delivery options. The logic mirrors the Python solution, using a loop to calculate the number of valid sequences for each step. Java-specific differences include explicit type declarations and the use of the final keyword for constants. The modulo operation is applied at each step to prevent overflow, and the result is returned as an integer. To solve the problem, let's begin with the simplest case where n equals 1. Here, we have only one pair of tasks, P1 for pickup and D1 for delivery. The result is initially set to 1, which serves as our base case, and we define a constant mod as 10 to the power of 9 plus 7 to handle large numbers. Since the range for the loop starts at 2, no iterations occur for n equals 1. The result remains 1, as there's only one possible valid sequence, first the pickup P1, then the delivery D1. Finally, we return the result, which is 1. Now, let's consider the case where n equals 2. Here, we have 2 pairs of tasks, P1 and D1, as well as P2 and D2. Just like before, the result is initialized to 1 and mod is set to 10 to the power of 9 plus 7. This time, we perform one iteration in the loop. When I equals 2, there are 3 positions for the new delivery task, D2, and 2 positions for the new pickup task, P2. Multiplying these gives us 6 possible arrangements for this step. We then multiply this by the current result, updating it to 6. After taking the modulo, the result remains 6. At the end of this process, we determine that there are 6 valid sequences in total for n equals 2. From the previous calculation, we know that the result for n equals 2 is 6. Moving on to n equals 3, we now have 3 pairs of tasks, P1 and D1, P2 and D2, and P3 and D3. As always, we start by initializing the result to 1 and setting mod to 10 to the power of 9 plus 7. With this setup, we are ready to calculate the total number of valid sequences step by step. For n equals 3, the first iteration happens when I equals 2. At this step, there are 3 positions for the delivery task D2 and 2 positions for the pickup task P2, leading to 6 possible arrangements. Multiplying this with the result, we update it to 6. After taking modulo, the result remains 6. In the second iteration, when I equals 3, there are 5 positions for the delivery task D3 and 3 positions for the pickup task P3, giving us 15 possible arrangements. Multiplying this by the current result of 6 updates it to 90. After taking modulo, the final result is 90. This means there are 90 valid sequences for n equals 3, which we then return as the output. To generalize this approach for any value of n, the formula for each iteration calculates 2 *I 1 *I and multiplies it with the running result. Taking modulo at each step ensures we handle large numbers efficiently. The reasoning behind this formula is that for the ith pair, there are 2 *I 1 positions to place the delivery and I positions for the pickup. By iteratively building the result, we cumulatively account for all valid sequences. This algorithm is highly efficient, running in O(n) time with O(1) space complexity. By leveraging this combinatorial method, we achieve both correctness and optimal performance for the problem. In analyzing the time complexity of our solution, we begin by breaking down each step. First, initializing constants like the mod value and setting the variable result to 1 are straightforward O(1) operations since they happen only once. Next, the core of the computation lies within the iterative loop, which runs from I equals 2 to I equals n. This means the loop executes n1 iterations. Within each iteration, we perform 2 key operations, calculating 2 *I 1 *I, which is a multiplication and happens in O(1) time, and then applying the modulo operation, result % equals mod, which is also O(1). Since both of these are constant time operations and they occur n1 times, the total time complexity contribution from the loop is O(n). Finally, the return statement, which outputs the computed result, is a simple O(1) operation. When we sum up all these steps, the overall time complexity of the solution is determined to be O(n). Now that we've established the time complexity, let's discuss the space complexity. The memory usage of this solution is minimal and depends on the variables used during execution. Specifically, constants like mod, the result variable, and the loop counter all require fixed, constant space. Additionally, there are no auxiliary data structures being used, such as arrays or stacks, and no recursive calls that would require extra memory allocation. Even intermediate computations like multiplication and modulo operations are performed in place without the need for additional storage. This ensures that the memory usage does not scale with the size of the input n. As a result, the total space complexity of this solution is O(1), which means it remains constant regardless of the number of pickup and delivery pairs. To provide a comparison, consider a brute force approach to solving this problem. A naive method would involve generating all possible permutations of the pickup and delivery tasks and then validating each sequence to check if it meets the problem's constraints. For n pairs, there are 2n possible permutations, and validating each sequence would require O(2n) time. This results in a staggering time complexity of O(2n). *2n, making it computationally impractical even for small values of n. In contrast, the optimized solution we've implemented avoids this inefficiency by leveraging mathematical properties of the problem. Instead of generating all permutations, it calculates the number of valid sequences iteratively, based on the available positions for new pickups and deliveries. This approach keeps the time complexity as O(n) as the loop runs n1 iterations with constant time operations in each step. Additionally, the space complexity remains O(1) because no extra memory is allocated, and all operations occur in place. This mathematical and iterative approach ensures both time and space efficiency, making it a highly effective solution. When solving this problem, there are several common mistakes that you should avoid. First, ensure that each pickup always occurs before its corresponding delivery. If you mix up this order, it violates the problem constraints and produces invalid sequences. To avoid this, you can track the pickups and deliveries systematically using a set or a stack to ensure correctness at each step. Next, using a brute force approach to generate all permutations of 2n actions without filtering invalid sequences early on is highly inefficient. Since the total number of permutations is factorial in size, this approach quickly becomes computationally expensive as n increases. A better alternative is to use a backtracking method, which generates only valid sequences from the start. Lastly, incorrect base cases in recursion can be a major pitfall. If you don't properly handle scenarios where there are no pickups or deliveries left, it can lead to infinite recursion or missed solutions. To prevent this, clearly define the termination condition, such as when all pickups and deliveries are successfully processed. Another mistake to watch out for is overlooking modulo arithmetic, especially in problems where results can grow extremely large. Large numbers can exceed integer limits, and many problems explicitly require results to be returned modulo 10 to the power of 9 plus 7. To ensure correctness, apply modulo operations consistently during your calculations, not just at the end. Additionally, failing to recognize the symmetry in this problem can lead to redundant computations. The relationship between smaller and larger cases often reveals useful patterns that can simplify the solution. For example, studying how sequences behave for lower values of n can help you identify combinatorial or dynamic programming relationships. By leveraging these patterns, you can optimize your approach and avoid treating each n as a unique problem to solve from scratch. In an interview setting, there are key approaches that will help you stand out when tackling this problem. One of the most important is to prioritize the constraints. Interviewers want to see if you can effectively enforce rules like ensuring all pickups occur before their corresponding deliveries. They also value solutions that are optimal. While brute force may be acceptable as a starting point, you are expected to refine your approach to handle larger inputs efficiently. Testing small cases is another valuable strategy for combinatorial problems. For example, trying n equals 2 or n equals 3 can reveal patterns that make the general solution clearer. If you choose to use recursion, it's critical to explain your base cases and recursive logic clearly to demonstrate your understanding. Finally, be prepared to discuss the trade-offs in your solution. For instance, does your approach optimize for time, space, or both? Being able to justify your choices is crucial in demonstrating your problem-solving skills. This problem also connects to several related problems, which can provide valuable insights in practice. For instance, LeetCode 22, generate parentheses, is another backtracking problem where you must generate valid sequences while adhering to constraints. Similarly, LeetCode 46, permutations, involves generating all permutations, which might be an intermediate step if you're exploring a brute force approach. Of course, LeetCode 1359 is directly related, as it focuses on counting valid pickup and delivery sequences rather than generating them. Finally, LeetCode 77, combinations, is useful for understanding how to systematically generate sequences while respecting specific constraints. Practicing these problems can help you develop the intuition and techniques needed to tackle similar combinatorial challenges more effectively. There are also multiple approaches to solving this problem, each with its own set of trade-offs. The backtracking method systematically generates valid sequences by avoiding invalid ones early, making it more efficient than brute force. However, it can still become computationally expensive as n grows larger. Dynamic programming is another option, where you build solutions for larger n using pre-computed results for smaller cases. This improves time complexity significantly, but it requires extra space and careful management of the state transitions. Finally, mathematical combinatorics offers the most time-efficient solution by directly calculating the number of valid sequences using formulas. While this approach eliminates the need for iteration or recursion, deriving the correct formula can be challenging and prone to mistakes. Each of these methods has its strengths and weaknesses, so understanding their trade-offs is essential for selecting the best approach depending on the problem context. Great job! To recap, we discussed the combinatorics-based problem of counting valid pickup and delivery sequences. We started with a brute force approach to build intuition, but acknowledged its limitations for large inputs. Key takeaways include the importance of understanding constraints and optimizing solutions for efficiency. Thanks for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!